everyone. Thank you for joining. Right. You can go ahead and just mute yourself upon joining, everyone. Welcome. Looks like a good group. Hey, Caitlin. Okay, I think we can kick it off. What do you think? Yeah. Sounds great. Amazing. Well, welcome everyone. Thank you for joining the Materials Interest Group speaker series. We have a great speaker today. If you were at the AATCC summit last year, you probably heard Haskell speak or met him and had a chance to connect with him. We are so happy and honored that he has come back to speak at our interest group. We have a few housekeeping. This is your session, so we encourage interaction. Please add your questions in the comments, and I will make sure to, at the end of the talk, I'll make sure to pitch it, and we'll talk about your questions. Please mute your mics so that there's no issue in trying to hear Haskell. During the Q&A, you can also raise your hand in addition to putting the questions in the chat. So if you'd like to ask him your question yourself, feel free to raise your hand. We are recording the session, so if you wish not to be recorded, please turn off and mute your webcam. I have a quick and short introduction of Haskell. Dr. Haskell Beckham is VP Innovation for Columbia Sportswear, driving innovation strategy, planning, and execution in apparel, footwear, and accessories. Prior to joining Columbia, Dr. Beckham was a principal scientist at Exponent, a leading scientific and engineering consulting firm, and a professor at Georgia Institute of Technology. Dr. Beckham has degrees in textile chemistry, BS Auburn, and in chemistry, PhD, MIT, with a focus on materials. He has served as a director on the Emerging Technologies Council of the Advanced Textile Association, ATA, and a member of the Executive Committee on Research for AATCC. He is the 2024 recipient of the only medal, AATC's highest scientific award. So that was amazing. Thank you so much for being here, Haskell. Do I have any more slides? I don't. Well, over to you.
All right. Thank you very much for that very kind intro. I'm excited to be here. Appreciate the invitation and the opportunity to talk about some work that we've been doing for the last 8 to 10 years, I would say, at Columbia Sportswear. I'm going to share my slides from my computer now, and then we'll get started with the presentation. Okay. So, hi, everybody. As Purvis said, my name is Haskell, and I'm coming to you from the Innovation Lab at Columbia Sportswear. We're headquartered in Portland, Oregon. Appreciate everyone joining in to listen to a few stories that I have to tell today. I've centered these stories around a topic I call multi-material textiles for thermal management. Before I get into the meat of the content, just for those of you who may not know, Columbia Sportswear is a brand headquartered in Portland, Oregon. We design, merchandise, and market apparel and footwear for all seasons and all activities. We have been around since 1938, and our founder, Gert Boyle, really it was her parents that founded the company, but Gert Boyle really made the company, and her son Tim, who's now our CEO, made the company what it is today and took it global. So you'll hear more from Gert later in the presentation. Our mission at Columbia is to unlock the outdoors for everyone, and we do that in a lot of different ways. The reason why that is our mission is because more and more research is showing that it's just good for us to go outside. I think for those of you who appreciate the outdoors, you already know this, but if you don't spend as much time outdoors as you should, then maybe you're unaware of some of the research that has been exploding in the last, I would say, 5 to 10 years. It's not just anecdotal stories in the popular press, but really good peer-reviewed research using geolocation data, statistical and very rigorous statistical analysis is showing correlations between spending time in the outdoors and a whole variety of health benefits. It's good for our physical and mental health. So we encourage all of you to go outside. And so at Columbia, we make products and we deliver messaging, make products to enable people to go outdoors and spend more time outdoors comfortably. And through our messaging, our marketing, we encourage people to go outdoors. Part of unlocking the outdoors for everyone means that we offer really high-performing products at prices that a large variety of our consumer base can afford. There are brands that offer products that really, from standard testing, shows that they're doing the same thing, but they're able to command higher price points. We offer value products across the entire price point range, and we focus our efforts in creating products to keep you warm when it's cold out, dry when it's rainy and wet out, cool when it's hot out, and protected from environmental hazards like sun overexposure or insect bites. In each one of these categories, we deliver our own innovations. One of the ways that we are able to deliver the products at the prices that we deliver the products at is because we have our own innovation group and our own innovation lab, and we develop all kinds of components, and these are primarily functional fabrics, which is what I'm going to be talking about today, or multi-material textiles to be more specific, but there are also things like outsole rubber compounds for the footwear and midsole cushioning compounds for the footwear as well. But these badges represent our branded innovations that our designers and developers use to put into the product line. Most of these are patented or protected via trade secrets, and so it's things that we have developed that's different than what the rest of the industry has access to. And because we don't tend to use what we call third-party ingredient brands, things like Gore-Tex, then we're able to pass that cost savings on to the consumer and thereby unlock the outdoors for more people, more consumers. So that's our story. And what I'm going to be telling you today is give you a couple of specific examples in terms of these functional fabrics that we've developed for thermal management, a couple in the warm category and one in the cool category. All right. So first of all, how do we do our work? We take a fundamental approach to this. We look at all different modes of heat transfer in cold environments, and that's convection, radiation, and conduction. And do the same thing when we're developing functional fabrics that go into our products to keep people cool when it's hot out. We look at radiation, convection, and conduction. And I would say the thing that probably distinguishes Columbia from many of our competitors is that we take a very, very fundamental and detailed examination of all three modes of heat transfer, not just convection and conduction. We do a good bit of thermal modeling, and so we fundamentally look at the equations, and then we use these to actually model different scenarios. And we have to, and when you do thermal modeling, You can generate numbers like this, for example, under a given different scenarios. In a cold environment, you can see heat loss occurs via perspiration, conduction, convection, radiation. And in a hot environment, when the temperature is warmer, then you got a lot of heat coming in, and in particular, that comes in via radiation. See, in both of these cases, whether it's a cold environment or a hot environment, the radiation component really shouldn't be ignored, right? And so I like to point out to folks that, for a long time in the industry, a lot of winter jackets, different forms of insulation, but they're all to us, they're just different forms of trapped air. And so as long as you've got an air impermeable shell fabric on that jacket, then you're working on the convection and conduction components. The conduction components because you're trapping that air, convection because you're keeping wind from penetrating the shell fabric. But for the most part, you're not really tackling the radiation component. And so that's really going to be the focus of the talk today when I talk about these multi-material textiles that we've developed. And we've taken explicit consideration fundamentally of the radiation component of heat transfer and allowed us to create materials that are really different to provide thermal management in different environments. You have to consider both solar radiation in both environments as well as thermal radiation. So I call it thermal radiation. It's basically the radiation coming off the body or coming from the environment. Solar radiation, as the name implies, is the radiation or heat transfer via radiative heat transfer from the sun. For solar radiation, that's considering radiative heat transfer from the UV through what's called the near IR range. And for thermal radiation, that's considered the mid to far IR range. And it's the sort of thing that if you use thermal imaging cameras, you can get a good indication of. And so I love showing this slide because you can see both curves, both the solar radiation curve and the thermal radiation curve. Thermal radiation curves are estimated or calculated at different temperatures. That's why they're so smooth. The solar radiation curve you see on the left is actually measured. You can see the noise there. You can see the dips due to absorption of different wavelengths of radiation coming from the sun due to the atmosphere, the molecules in the atmosphere, which will absorb at different wavelengths. So. And then if you look on the bottom left there, you can see, which I think is quite interesting, UV is 3.3% of solar power. But then the visible is the most of the solar power, but the near IR is actually a very significant component of solar power as well. So most people might say, well, it's the visible and the near IR that's leading to the heat. Well, the whole thing can be converted to heat if it absorbs from the UV through the near IR, but since the UV component is so small, it doesn't really do that much in terms of heat generation. It's really the visible and the near IR. All right. So in cold environments, for example, you might want to reflect or deflect solar radiation because that's really adding a lot of extra heat onto the garments that people wear and onto the skin if you're not wearing garments. But that's in warm environments. But in cold environments, you may want to take advantage of the fact that you've got this great heater up in the sky that you can absorb heat from and help put products together to take advantage of that. And then for thermal radiation, in a cold environment, you want to trap that. You don't want to lose that to the cold environment. But in a hot environment, you really want that to emit as efficiently as possible. And you can put collections of materials together that actually do a better job of this than the standard fibers and textiles that we're all accustomed to. And that's what we've done at Columbia, and that's what I'm going to be talking about now. So in order to do this, and we had, as opposed to just putting a bunch of materials together and then to seeing what that does in terms of the warmth, as I said, we take a fundamental approach. And so I'm really interested in understanding how different material combinations absorb, transmit, and reflect across that entire spectral range. Because it's such a broad range, from solar, you're going from UV to near IR, and for the thermal range, you're going from all the way out to some 30 or 40 microns. There's not a single instrument that you can use to do that. And so we've put together this optical bench that we used in order to quantify as a function of wavelength, how much of that radiation is, again, absorbed, transmitted, and reflected, because you need to consider all of that. And because you need to consider all of that, and you usually have to do more than one experiment in order to collect all the data. And you also need to use integrating spheres. So you can see in some of these optical benches that you're looking at that we use integrating spheres to collect all the radiation. So both diffuse as well as specular reflection. And we played little tricks in terms of the measurement methods so that we can actually determine the full, not only full spectrum, but the full effect for a given wavelength, whether the radiation is absorbed, transmitted, or reflected. Right. This, for example, is some details about how we do some of those measurements for some of the integrating spheres across UV on the left, near IR in the middle, and then the mid to the far IR on the right. All right. So that's a little bit of background and some insight into the approach that we take. And now I'm going to give some examples of some of the materials that we've developed by using those methods and techniques, and show some results about how they work. And so the first example I'm showing is for something to keep people warm when it's cold out. We call this Omni Heat. You're looking at it now. That's a jacket, and that's a heat reflective liner on the inside. And that's Columbia's had that in the line since 2010, so 15 years and counting. Been tremendously successful for the brand. It's metal attached to the surface of a textile, but in a discontinuous fashion, because metal itself, if you were to cover the entire surface of the textile with a sheet of metal, it wouldn't breathe anymore. Those of you, if you look at potato chip bags, and you look inside, oftentimes you'll see a metallic layer, and that's used for food packaging because it's a very good barrier material, because molecules like oxygen and water can't get through a thin metallic layer because it's atomically uniform. So it's a very good barrier layer. Well, we don't want that in our textiles because the human's body is constantly giving off moisture. And so we need these fabrics to breathe. And so we have, in this particular example, we have this in a pattern of dots. And so the moisture can still get through the lining fabric on these jackets in between the metallic dots. So it's still breathable. All right. And so that's we call this Omni Heat Reflective. It was originally inspired by radiation used in spacecraft. It's now used for emergency thermal blankets, for folks who spend time in the outdoors, but it's obviously still a very important component of a spacecraft because there's no air in space, and so radiative heat transfer is a very prominent mode of heat transfer. Temperatures in space typically vary from minus 250 Fahrenheit to plus 250 Fahrenheit, and that simply depends on whether you're in the sun or not in the sun. So and it's challenging for spacecraft too, and I'm telling you this because at the end of this presentation, I'm going to talk about a partnership with a space exploration company that we've been involved in for quite a few years now. But for spacecraft leaving the Earth and going to the moon, the part of the spacecraft that faces the sun gets hot, and the part of the spacecraft that doesn't gets very cold, and the temperature differences are quite broad. And so it's managing thermal energy on spacecraft is a very challenging field indeed. And so more on that in just a second. So the idea for the original Omni Heat came from the materials used in spacecraft, and those are primarily just vapor deposited aluminum on plastic films. They tend to be polyimides like Kapton or polyesters like Mylar, and they're used for different locations. And it's not just a single layer on spacecraft. They tend to be multiple layers. They're called MLI blankets, or multi-layer insulation blankets. And the number of layers are dictated by what kind of thermal insulation you need for different parts of the spacecraft. So, all right, more on that in a second. So at Columbia, our founder, Gert Poyle, was very fond of saying it's perfect now, make it better. And so that really drives a lot of the innovation work that we do at the company. And so despite the success of OmniHeat, as I said, has been in the market for some 15 years. 4 years ago, we launched a new version of that we call OmniHeat Infinity. It's the same material, it's aluminum, it's a metal deposited to the surface because this radiative heat transfer is dictated by the surface properties of a material. And so metals have different properties from ceramics, which have different properties from polymers in terms of their thermal radiative heat absorption, emission, transmission, and reflection. And so metals are really good at reflecting radiant heat, and that's why we're using for a heat reflective lining here. The difference between this version of OmniHeat and the original version of OmniHeat, number one, it's obviously gold, and we did that just so consumers could see the difference in that. And so it's still aluminum, but there's a very thin protective polymeric coating on top of the metal where that contains a pigment, a gold pigment. Because if you look at the materials used in the space industry, you'll see as much gold as you see silver. So we made this one gold, but it works better because we increase the surface coverage of the metal. During the course of development of the material, we actually applied metal to the surface of textiles as a function of surface for different surface concentrations, and determined that it's a nearly linear relationship. And so what you see here, those are actual data points. That's not a model. That's radiant heat reflected on the y-axis as a function of the percent coverage that you see along the horizontal or x-axis there. And going from OmniHeat Infinity, which is about 50% surface coverage from the original version, which had 30% surface coverage, we have about a 40% increase in radiant heat reflection. And so that's helpful because once we have a heat reflective lining like that, then we can put jackets together that have less standard insulation in the middle layer, and so we can create products that provide warmth at lower weight or lower volume, which is the goal. The moisture vapor transfer is nearly the same. We did those studies as well where we measured MBTR as a function of the percent. This is MBTR on the y-axis or the vertical axis here. It's a function of percent coverage on the horizontal axis. And you can see the new version and the original version is nearly the same. It's not until you really get to high coverages that you start to really kill the breathability, which kind of makes sense. It's not this moisture vapor transfer. It's not a convective flow, and so moisture will find its way through a film-like material as long as there are avenues for it to get through. One of the things we had to do, though, since we wanted to make it gold to distinguish it from the original version, which was silver, is make sure that the pigment we put in that protective coating on top of the metal did not significantly reduce the reflectance. And so here you see reflectance over 5 to 40 microns, so the thermal range. Remember, this peaks around 10 microns. That's the thermal range coming off the body, the thermal radiation coming off the body. And you can see that it still has, even though we have a gold pigment in that protective layer now, the reflectance is still very high. It's 88% compared to 89, 90% for the silver, right? All right, so that's the first example. The second example I want to talk about in terms of a textile multi-material came about when we started looking around at extreme environments on Earth, and to try to figure out, to try to look for inspiration for keeping people warmer in really cold environments. And so we looked at the Arctic or the polar regions, and in the Arctic in particular, these magnificent animals live. Not only survive, but thrive. These are obviously polar bears. And if you Google polar bear pelts and how they stay warm in such cold environments, there's all kinds of information you'll dig up on the internet. We dug into the scientific literature as well, and to our surprise, there seemed to be some disagreement, even in the scientific literature, about how those pelts work. The conventional wisdom says that they're translucent and they let sunlight penetrate and absorb into their skin and absorbs in their skin, which is pigmented, is darkly pigmented. And so I thought that was interesting. I also thought that the disagreements we ran into in the scientific literature were interesting. And so I thought, well, we need to get our hands on a polar bear pelt and apply all these tools and methods we've developed here at Columbia Sportswear to understand the relationship between solar and thermal radiation in a polar bear pelt, because that may lend some insight that we can use to actually make better jackets to keep people warm in cold environments. And so my first stop, was the Oregon Zoo right here in Portland. I went up to the gate and I said, I got to talk to your polar bear keepers. And they said, who the heck are you? And why do you want to talk to our polar bear keepers? And after I explained to them who I was and why I wanted to do it, they actually put me in contact with people who put me in contact with people who put me in contact with people at the Burke Museum of Natural History. Now, this museum is on the campus of the University of Washington up in Seattle, so about a 3-hour drive from Portland. And so I emailed the director there, and I explained who I was. I said, I'd like to know if you have a polar bear pelt, because we'd like to study it to understand its interaction with solar and thermal radiation, because of gaps we see in the scientific literature, and we'd like to maybe use that information for the work we do here at Columbia Sportswear. And they immediately said, yes, we have a pelt. When do you want to pick it up? I said, I'll be there tomorrow. So I drove up to Seattle and picked up that polar bear pelt, which you see there on the right. And that's an amazing museum. For those of you who, I don't know if anyone is online who is from Seattle, but even if you're not, if you find yourself in Seattle, I highly recommend visiting this museum. It's on the campus. It's built and designed. You can actually almost get into the stacks themselves. If you look in the background on that picture on the right, you see a lot of other cool stuff there too. But it's a teaching and research museum, and you really get immersed in that just as a visitor, a regular visitor when you go there. Anyway, awesome museum, highly recommended. We borrowed a polar bear pelt, brought it back to Columbia, and started to apply these tools and techniques, including using a solar simulator that we have in the lab, to try to understand fundamentally how that polar bear pelt works to keep those bears warm in such cold environments. And so on the left, you'll see we have a lot of great equipment in our lab here in Portland, but we don't have a giant environmental chamber. So we went down to the University of Oregon and used their environmental chamber, took the pelt down there and cranked the temperatures down as low as it would go, took our thermal camera, thermal flux sensors, hot plates that we would set at room temperature, thermocouples, solar simulator, and we did all of our studies both in the lab and at low temperatures down at the University of Oregon in the Bowerman Sports Science Center. All right, and so before I get to the results, I just want to say, what we discovered about those polar bear pelts was quite interesting and actually different from what the conventional wisdom says. We were given permission to make some very minor modifications to that pelt, which allowed us to determine that for the majority of the pelt, sunlight can't get through the fur all the way down to the skin. And so the pigmentation of the skin itself, even though that helps with solar absorption, if it's darkly pigmented versus not, isn't really what the conventional wisdom says it is. And so that seemed interesting enough, at least for the folks who study polar bears, that we went to the trouble to write this up. Had some help with some former colleagues of mine from Exponent to get that in the literature. What we did learn, though, what's really critically important is sort of the fiber density of the upper layers. And so it turns out the pelt, for the majority, the fibers of that pelt, for the majority of the pelt, are dense enough that sunlight can't get all the way down to the skin. It does deposit heat, of course, wherever it absorbs, but it can't get all the way to the darkly pigmented skin. So it's not, the polar bear pelt isn't as efficient as some might think, some of the conventional wisdom thinks that it is. And that's what this publication was about. We actually used the information that we discovered during those studies and put together a new line, a new technology we call OmniHeat Arctic that launched last fall. We had some fleece versions and we had some puffer versions. You see the fleece on the left, the puffer on the right. The fleece was quite simple, and it's not something that we can own in terms of a patent because if you look in the hood region, you see how it's darker on the inside and lighter on the outside. Basically, if you just have a gradient of fiber density and solar absorptivity as you go from outside to the inside, you can create that polar bear effect on a fleece, and that's what we've done for some of the fleeces. I want to focus really on the right, though, because this particular construction is very effective. If you look at the lining on that jacket, there's a patterned black lining. There's a special textile multi-material. Again, we call this OmniHeat Arctic. Those black dots and triangles are a metallic layer on the textile, but on top of the protective layer on top of the metal, we put a black pigment into that protective layer. And that black pigment allows for very high solar absorptivity into that layer. And so here's a material, because the layers are very thin and it's metallic, that exhibits low thermal emissivity because of the metal, and because of the darkly pigmented protective layer on top, it exhibits high solar absorptivity. And so when you use this as a lining in the jacket, you can create a construction and use a shell fabric and a standard insulation layer above it that allows sunlight to penetrate all the way to the lining of the jacket. You have a situation that mimics what most people think polar bear pelts do. But it doesn't do, as I described very briefly. It doesn't do it as well as I think some people think it does, but it's a material that allows sunlight to penetrate, absorbs it close to the body, and once it absorbs and gets converted to heat next to the body, is now protected from the cold environment by the insulation layer above it that it just transmitted through to get to the lining. So I'll show some data in a second. I'll just say that particular technology, we actually launched it as a product back in 2020. That is a metal on top of a fabric, with a protective layer on top of the metal that contained a black pigment. We called it OmniHeat Black Dot. It acted both as a heat shield because it exhibits low thermal emissivity, but also as a heat magnet because it exhibits high solar absorptivity. And that combination was definitely an industry first. And so we had that in the line for a few seasons. It's no longer in the line, but it made for some very effective cold weather jackets, because for radiative heat transfer, there's a very strong dependence on the temperature difference between one surface and the next surface. And at the shell of a jacket, that's where you've got the highest thermal gradient between the shell and the external environment. If you're in a cold environment, the temperature from your skin all the way out slowly goes down, but the biggest drop in temperature is from the shell fabric into the environment. So if you can change that shell fabric to have it for it to be low emissivity, which is actually what we've done here, then you can have a very effective jacket in terms of retaining more heat and being warmer. All right. So here's some of the test results from the OmniHeat Arctic that we collected in the cold chamber. We use a solar simulator and a hot plate underneath that we set at skin temperature, and we stack materials up. When we use a lining that's the OmniHeat Arctic, then you'll see we have a heat flux sensor underneath. You can see that we get net heating when the sun is on. So this testing was done at 0 degrees C under a solar simulator, and you're constantly absorbing more heat from this solar simulator for these material stacks. Compare that to a regular black jacket, and this is a little bit counterintuitive, I believe, but a regular black jacket with a regular density shell fabric, you get the sunlight absorbed at the surface of the jacket. Well, once the heat is deposited at the surface of the jacket, you're right next to the cold environment, so it can emit right back into the cold environment, and you lose that heat. You don't take advantage of it as much. And so the OmniHeat Arctic is using Shell fabrics and regular insulation allow solar penetration to absorb on a particularly high solar absorptive lining fabric and traps that heat. So you can actually put jackets together that take advantage of solar heat gain in a way that I haven't seen other constructions do. So that's the technology. And I had some of my colleagues say, "Well, Haskell, of course it's warmer in the sun. Everything's warmer in the sun." I said, "Well, no, that's not necessarily true. If you take some of our regular black jackets, and you put it in the sun, it's not going to be warmer because you think of the shell fabric, the fabric right next to the environment, that's basically blocking the sun from getting into the jacket and depositing that heat deeper into the insulation layer, ideally all the way down to the lining layer." Even when we don't use sunlight, though, and we compare, I've blocked out, my legal team doesn't want me, poking our competitors. So I've blocked out who the competitors are at the bottom of these plots. But here's thermal resistance. This is standard hot plate testing. But that Omni-Heat Arctic jacket is lighter and it's warmer even without the sunlight. And it does that because the lining itself exhibits low thermal emissivity. Here's what that looks like using a thermal imaging system. So here it is. We put it on a hot plate, put the jacket on a hot plate, set it at skin temperature, and we're using a thermal imaging camera on top of it. And you see the black triangles and dots, which is where the technology is. That's the multi-material. That's metal with a protective layer on top that contains the black pigment. You can see that's blue. So heat is not radiating out of that. But it is radiating out through in the spaces in between, which is the regular textile. And so again, great visual demonstration of how those linings really protect your heat. And then because of the construction of the jacket itself and that protective layer with the pigment on top, you absorb the solar energy. So great technology. So that's two for warm. And now I'm going to switch gears and talk about how we can use this approach in textile multi-materials to keep people cooler in hot environments. And this, by the way, as we all know, it's a hot and warming planet. And so this is a really important topic and one that we spend a tremendous amount of time on working on. The product I'm going to talk to you about now, we've actually had it in the market for a few years. It's called Omni-Shade Sun Deflector, and it's nothing more than titanium dioxide dots printed on the outside of a fabric. It mitigates the heat buildup and it also protects against UV. Now, titanium dioxide is a ceramic, and so in this case, the textile multi-material is the textile with a ceramic that's printed on the surface. The titanium dioxide is basically sand with titanium instead of silicon. So there's a binder there as well, right? So we have to use a binder that holds the titanium dioxide particles together, and that's put in the form of a foil that's transferred to the surface of the fabric. It's a common active ingredient in sunscreens, for example. So it does provide some protection against UV, but it really is the fabric structure itself that's provided most of the protection, because like with the application of the metal to the textile that I just talked about with the Omni-Heat products, for this, we don't cover the entire surface of the fabric. We apply it in a discontinuous pattern. In this case, it's also dots. You have a picture there. Yeah, you can see it there. But if you look closely, you can actually see this is a very different kind of material applied to the surface of the fabric. But we apply our methods. Here's solar reflectance, and this is where we get the biggest effect. White dots. This is basically the base fabric with and without the white titanium dioxide dots on there. Here I've shown data for the UV invisible region only, as well as the full solar region. You can see, in fact, if you look at the plots on the left, that's reflectance versus wavelength. We get a lot more reflectance in the visible range, but we also get more reflectance in the near IR range as well. You can integrate across those wavelengths to get a number, and that's what the numbers are you see in the table there, 24.5% versus 6.8%. But that's not the only way this technology helps in terms of keeping you cooler. It also limits transmittance. And so the human skin has a very high solar absorptivity. And so anything you put to limit transmission through the fabric to absorb into the skin will actually keep you cooler as well. And so the solar deflector material has a lower transmittance than the base fabric, so that helps. It also has a higher thermal emittance than the base fabric itself. So it's about 3% difference. This is the thermal range. Notice this is emittance versus wavelength at the bottom. But all of these things add up to provide a cooling effect. Here's another example of how we tested this technology. In this case, we took some Tupperware buckets and put water in them because skin is highly hydrated. So this was our simulation for skin, and we just put base fabric plus OmniShade sun deflector and base fabric plus OmniHeat reflective metal on top. So we got two textile multi-materials there compared against the base fabric with the sun deflector, the titanium dioxide, the ceramic in the middle, and then the metal which is aluminum, or the OmniHeat reflective on the right. And you can see over time that the base fabric with the ceramic actually does better. Now, OmniHeat reflective, metals are good at reflecting solar, but they're not good at emitting thermal. They're the exact opposite, right? And so whereas metals, and I have seen brands in the past put shiny metallic coatings on the outside of fabrics to keep you cooler, and it does work to some extent, but it doesn't work as well as ceramic materials do, because ceramics have high thermal emittance, and if they're white, they can have high solar reflectance. And what you want to keep cool is a material that has high solar reflectance plus high thermal emittance. That's ceramics, not metals. Metals have low thermal emittance, and so that takes me to this partnership we have with a with a space exploration company out of Houston, Texas, called Intuitive Machines. In the spring of 2021, this company approached us looking for sponsorships because they were building this robotic spacecraft to land on the surface of the moon as part of the build-up to the Artemis missions. And for those of you who've been paying attention to what NASA is doing, so Artemis is the names of the missions to put people back on the moon and beyond. But before that, they're funding lots of little companies that are putting robotic landers onto the surface of the moon to conduct all kinds of experiments in preparation for putting people back up there. So Intuitive Machines approached us. Very quickly, we realized that in addition, more than just a sponsor, because we had these materials and knew about their thermal properties at a very fundamental level, that we could speak the same language that their thermal engineers spoke. And so it very quickly became more than just a sponsorship, but a scientific partnership. And so that started in 2021. We entered into that partnership for a number of reasons. Number one, the main reason was we knew it would be very, very interesting to work closely with the thermal engineers and scientists who were working on that spacecraft, because we would learn about materials and methods and processes, and that's exactly what happened. Some of the information that we learned by working with them, we brought back to the lab here in Portland, put together some materials, and actually launched some jackets into the marketplace that, on a per weight basis, are definitely the warmest jackets that Columbia's ever put together. So it's been an amazing partnership. The space is hard, and so even though originally the spacecraft was supposed to take off and land in 2021, it wasn't until 2024, but it did go up and it did land on the moon. And landing wasn't perfect, but it was definitely good enough for all of this payloads to get all the data down, and so it was deemed a huge success. And so that was the first mission. That was last year. I had the privilege of of being at the Intuitive Machines headquarters in Houston, Texas for the landing. This was the scene right after the announcement came that the equipment had landed on the moon. You know, there was a moment there as spacecraft approached the surface of the moon where you don't have any communication and you're just waiting. And in that room, you could have heard a pin drop. These are mostly scientists and engineers who had been spent years working on this project, right? And of course, their success or failure was coming down to this single moment. And so the room was just deadly quiet and deadly still. And then when the announcement came that the equipment had landed on the moon and it was communicating with mission control, the room just erupted. I'm getting chill bumps just retelling the story now, but it was, anyways, it's definitely something that's fun to be a part of and actually quite productive. And so it's fun. So we actually worked with them on a second mission as well. The second mission not only contained our original material, our metallic material that keeps things, you know, what's originally inspired by the materials used on spacecraft anyway, but also contained this sun deflector material. And in fact, Intuitive Machines and other companies in the aerospace industry are quite interested in this material because right now, in order to dump heat, they use paint, the white paints on spacecraft and also on the International Space Station, anything that's up in space, because as I described at the beginning of this presentation, you know, in space, you either need to reflect heat and get rid of it, or you need to dump heat because you're either really hot or really cold, depending on whether you're facing the sun or not, or just facing outer space. And so the sun deflector material is of a lot of interest because the current paints that they use are very expensive, have a short shelf life, and are very difficult to apply in a uniform manner on these complex surfaces as they build these spacecraft. And so for the materials that we put together, we can put a space-approved pressure-sensitive adhesive on the back, and it's quite easy to apply a fabric that contains this TiO2, the sun deflector material. And so on the mission that launched earlier this year in 2025, we had OmniHeat Infinity, which is integrated more deeply into the spacecraft and more broadly. And we added the second material, sun deflector, as well. Unfortunately, for the second mission, it didn't land as well, and so we weren't able to get the mission wasn't deemed a success. We weren't able to get all the information down for all the payloads which are on the outside of that vehicle. But the materials for all the data that we have from the spacecraft indicate that the materials behaved as expected, and we are currently still working with Intuitive Machines on a third mission, and we're working on them primarily with the sun deflector material to see if we can actually integrate that even more. All right. And so here's a selfie for the last mission. This is a spacecraft heading away from Earth, and you can see the Intuitive Machines logo, and underneath that you see the Columbia logo, which our CEO and marketing department was quite excited about, as you can imagine, just above the U.S. flag and the NASA logo. And I've got one more thing to show, and then we'll open it up for questions, but I've got a video that talks a little bit about, it's a mashup. It talks a little bit about the history of Columbia, about our innovations, why we innovate, and what we innovate. And then that leads directly into this partnership with Intuitive Machines, gives you a little bit more details about that through the eyes of the leaders at Intuitive Machines. And so I'll play that now, and then on the backside we'll be done, and we'll start with questions.
It's perfect.
Sorry.
Now make.
Sorry about that.
It's perfect. Now make it better.
That's what our late founder, Gert Boyle, told us. It was a directive to never stop improving our products, improving our technology, and improving where we play. But how do you know when something is finally perfect? Will it ever be perfect? How will we know when we're done? Today, you know Columbia as a global leader in innovative outdoor gear. But when we started back in 1938, we made one thing: hats. We made dress hats, hunting hats, swimming caps, and people liked them too. But we weren't comfortable being a hat company, even if we were a darn good hat company. So we expanded into apparel, and in 1962 invented the Henry's Fork fishing vest, solving problems for anglers everywhere. Were we done? If we were, you wouldn't have met the Bugaboo Parka in 1984, or popular 3-in-1 jackets that saved skiers everywhere from bulky layering, and saved them a few bucks too. But we still weren't done. Soon after we got to your feet, we engineered world-class footwear that keeps you safe and comfortable on the trail, on the deck, and in the snow. But no, not done. We kept on finding things we could make better, creating new innovations along the way. All of these Columbia innovations began by identifying a problem, finding a groundbreaking solution, and engineering that solution even better to unlock the outdoors for everyone. We are constantly researching, developing, testing, and releasing new innovations. These proprietary technologies and designs become the key ingredients in our award-winning products to keep you warm, dry, cool, and protected in the outdoors. From OutDry Extreme, our waterproof tech that never wets out, to OmniFreeze Zero, which works with your own body to keep you cool in the heat, and OmniHeat Infinity, a thermal reflective fabric that has literally been to the moon. We've tested our innovations and products in some of the harshest environments on Earth, but going to the moon is new for us. By testing in that harsh environment, we're gaining new insights to make our customers more comfortable here on Earth. I like solving problems. I like finding problems to solve. That's one of the reasons I love working with Intuitive Machines, because they're just my people, a bunch of scientists and engineers constantly solving problems to try to put something really amazing together.
What's really interesting about Intuitive Machines is we were given a task to do something that's never been done before. And so what we've done is built a community of suppliers, of partners that have been through this experience at least once. And as we continue looking at Mission 2, Mission 3, and subsequent, working together, we work as one team.
In the past, everything had been in a silo. And then you realize that other industries have so much to offer, and you break down those barriers and you start seeing a fusion across technology that can accelerate space exploration. That's what's exciting, where you're looking at the front of our lander, looks just like my jacket. Well, that's because I have the most efficient jacket on the planet, because we're working together and we're using all the resources across industries to really move faster. It's where we can use new technologies in an incredibly extreme environment, and we can tame those extremes.
The thing I hate about spacecraft is you've got some parts that want to stay warm and some parts that want to stay cold, and they're never besides each other, and you never can share the heat. The helium tanks want to stay warm. They want to stay energetic, so we have good pressure on the helium, and that pressure from the helium is what we use to push the methane and the oxygen from the tanks into the engine. So we're going to coat the helium tanks with these multi-layer insulation blankets to try to do passive insulation to manage that problem. We found that the OmniHeat material was very, very good for that.
With IM2, Sun Deflector regulates that thermal environment so that we are more capable of staying in an orientation that is optimized for communications and data back to Earth.
Whenever people try to do things that are very hard technically, you push the envelope in terms of what's possible. Those limits, the ones we think are holding us back, actually reveal what we're truly capable of. Every challenge we overcome doesn't just solve a problem, it expands what's possible for the future.
All right, thank you very much. That is it for me, and I'm happy to entertain any questions. I think I went a little long, so hopefully some of you can hang around for a little while if you have any questions.
Thank you, Haskell. That was really, really good. I especially like the fact that the partnership is really crossing different industries. So that was a fun way. So next time when someone's like, what can I do with my textile degree? It's like, you can go to space with it. So that's pretty cool. I added a note in the chat. Feel free to populate that with your questions. I'll kick it off with some of mine. I know this was a very interesting partnership that you've had with Intuitive Machines. Can you talk about any other inventions where Columbia was trying to develop for a certain demographic, and then there was those fabrics started being used in a different industry or a different application, or you got feedback that, hey, I like this such and such jacket because of a totally different thing that you guys had never thought about?
Yeah, so we do get questions a lot because some of our stuff is pretty unique, right? Especially a lot of the heat reflective materials. For example, in the military, we've worked in the military, NASA. I mean, we've talked to and worked with and done sort of demonstration projects with a lot of different groups, but nothing to the extent of that of what we've done with Intuitive Machines, right? And so just a little bit else about that. Intuitive Machines as part of the commercialization of space, right? What NASA is doing is trying to get small companies via grants, giving them grants, or in order they're trying to get them viable and develop the space economy, because when a large bureaucracy like a government does things, it tends to be a lot more expensive, right? And so they're working off fixed contracts. And so when we started talking to them, one of the things that we're very excited about was, our materials, that material that went up on that first mission and on the second mission, first of all, we were prepared to change our material to meet the specs required for space travel, because they are different than what our normal minimum specifications are for a jacket, right? No surprise there. Turns out we could use the same material, but that's a polyester fabric. And so that's commodity, and the way we're applying the metal, it's all commodity. And so they were working on a fixed contract, and they were using legacy materials for that spacecraft. They were super excited that we had options for them that won't break the bank. And so there are definitely options out there in terms of value engineering, cost engineering, as long as it performs and is durable enough for the kinds of environments that you're going for. Kind of a long answer to your question, but we have talked to people, but I can't think of a better example than the Intuitive Machines example right now.
Yeah. Another question I had was when you talked about the heat balance and how we gain heat and we lose heat, there was a certain article that I'd read in the past that I know evaporation or evaporative cooling also takes a role in heat loss. How does the Omni technology essentially interact with evaporative cooling?
Yeah, no, it's a great question, and it's a really important mode of heat transfer. And we have in our line what we call sweat activated cooling materials, and other brands have them as well, right? I mean, in fact, if you think about wicking fabrics, that spreads the moisture, allows for more efficient evaporation and cooling. But my point to people is, well, if you're sweating, that means you're already hot, right?
Right.
And so it does play a role, but it's it's the body's natural mechanism for cooling. It's why dogs pant. I mean, in an interesting example, kangaroos lick their forearms, right, or to enhance evaporative cooling. It's in the plant world, it's called transpiration, to keep plants sort of cool and protected as you get evaporative cooling when water evaporates through leaves. And so, yes, very important mode of cooling. We have something we call Omni Wick Evap. We have Omni Freeze Zero. We have all these branded technologies that take advantage of that. But again, if you're already sweating, you're already hot. So if you can figure out a way to do it before you start sweating, then you've got something.
That's great. We have a question here from Ravi, what kind of testing you mentioned had to put the material for space use? You mentioned that you had some modifications to support space needs. Is it density that was the main change?
Yeah, so for the space, so what I was saying was when we started working with them, we were completely prepared to change the material and make a special material. So the first step was to test our existing material, right? And the testing you have to do for something that's going to go to space, you had to do thermal. First of all, you had to test it thermal extremes. We don't normally have to test that. We had to go to plus 250 Fahrenheit to minus 250 Fahrenheit. Obviously, for jacket materials or clothing materials, you don't typically test at those extremes because we needed to make sure that the metallic dots weren't going to fall off. That wasn't going to, something bad wasn't going to happen to the structure of the fabric. Blah blah blah. So we had to do that repeatedly because whether you're in the sun or not in the sun in space, you'll see these extremes repeatedly as you're going from Earth to the surface of the moon. So we had to do that. The other testing that we had to do was we had to put it in a vacuum to make sure that there wasn't any volatiles coming off that could condense on some sensitive thermal or optical surface of the spacecraft and mess something up, right? And so we tested our material, which is a regular woven polyester fabric using a lining in the jacket with the technology, the metal applied to the surface, and it passed all of those tests. And so we didn't have to make any modifications at all, which our marketing department loved because they could, last year when this was happening, they could say, that material on that spacecraft that's helping keep that spacecraft protected from the extremes is the same exact material that's in your jacket. So that was easy.
That's incredible. Yeah, that is, like you said, good fortune that with testing all of it. Poipu has a question. Thank you, Dr. Haskell, for the talk. Could you explain how, sorry, the question moved away. Could you explain how the thickness of the air gap between the skin and clothing might affect the effectiveness of Omni Heat?
That is a great question. I can tell it's coming from someone who's understanding what we're doing here. Yeah, that's critical. There has to be an air gap. If there's not an air gap, and you've got metal or plastic touching, the skin or the layer that's on top of the skin, then you end up getting conduction. You don't get reflection, right? So you got to have an air gap. And what's been interesting to us over the years, because we put this stuff not only in jackets, we put it in hats and gloves, and we also put it in base layers. Well, base layers are pretty tight to the skin. Consumers love it. And, we've never really fully dug into why they love it so much because we're selling base layers. And so that's good enough for us. But if you look at skin, people have hair on their arms. Some people have hair on their skin. They're wrinkles, there are cracks, there's all kinds of different ways you can have an air gap, but you do need to have an air gap. That's really, really important for there to be reflection, right? You can also have conduction across an air gap too. And so whenever you have conductive heat loss, then that's not what you want, right? Because you got heat going out. You really want the reflection, which increases the thermal resistance. And so the more conduction you have, so the less air gap you have, the less effective it is. Great question.
Thank you. Tina had the next question. Through your partnership with Intuitive Machines, the materials were used on the equipment on the machine. Will there be an opportunity to use the same tech to improve spacesuits for passengers?
Yeah. So we get this question a lot because we're a clothing company, right? You guys are protecting a spacecraft. You make clothing. How come you're not working on the spacesuit? The only thing I can tell you is that other people have those contracts. But we have talked to NASA, for example, who have considered the materials. The only thing I will say is that these kinds of materials, whether they're ours or someone else's, will be used on spacesuits if it makes sense to use them on spacesuits, right? So, good question.
Sounds good. Katina asks, I'm curious to know if you tested human subjects in the Omni Heat products, if you saw any peculiar trends in full body movement versus static conditions.
Well, so everything that we do a lot of lab testing, but nothing goes to market before us obviously making prototypes, getting it on people and getting them outside. So we do have an entire product wear testing, field testing team. We don't quantify that so much as that becomes perception at that stage. And we'll compare against jackets without the technology or competitor jackets. So I don't really have anything quantitative to report there, but these people are out skiing and climbing mountains or snowboarding or just hiking in the gear and comparing it against competitor jackets or our jacket without the technology, and the feedback is coming back positive, and that's what leads to a market launch.
That's great. Next question is by Cole. When working on innovative technical projects, how do you and your team prioritize aesthetics for consumers? Is it a back and forth process, or does technical ability maintain priority?
Great question. Technical does not maintain priority. As I like to tell people, even engineers and scientists like to look good. And what I've learned in my time in the industry and working here is that you can have the best technology in the world. I gave you a little glimpse about Omni Heat Black Dot. That stuff worked great. Really, really impressive technology. Won an award, but it didn't sell because not everyone wants a jacket with black dots on the outside. So I'm fortunate to work for a company that's willing to try things, right? But if it doesn't sell, and usually that's for aesthetic reasons or fit or feel, right? I think the most important things I've learned are feel, fit, appearance, right? Then yeah, it doesn't work. So a common definition for innovation is invention plus commercialization. And so we invent quite a lot here in the lab, but we only commercialize 1 or 2 things a year. And so aesthetic always is the most important thing for sure. Aesthetic and also hand feel.
That's great.
And fit is super critical. And we all know that, right? I don't have to say that. If stuff doesn't fit right, if you don't look good in it, then most people aren't going to buy it. So
yeah. Next question
in fact,
is.
Sorry, just one more thing. We have, in my mind, the most advanced, best waterproof breathable technology on the market. We've had it out there forever. It's membrane outside as opposed to membrane inside, which is what Gore-Tex started and does. And we launched it originally. It was the first. We also won tons of awards. Outside Magazine listed it one of the top 40. We call it Outdoor Extreme. Outside Magazine listed it in 2017 one of the top inventions ever, and made the list along with duct tape and the Swiss Army knife. And it made that list because it was the first waterproof breathable jacket to eliminate PFAS chemicals from the outside. Because when you put a hydrophobic membrane on the outside of a fabric membrane laminate, you didn't need the PFAS anymore because it was already hydrophobic on the outside. But that was not a commercial success, and I had people who knew better, who understood what a great technology that was, and said, yeah, I didn't like the colors it came in, right? So just another answer to the question about, does technology or aesthetics rule the day? Aesthetics always rules the day in this industry.
That's a good point. Next question is, do you anticipate Columbia will be interested in exploring alternative sources of quantum dots, maybe using a circular sustainable approach, as well as different coding or deposition methods in the future? Additionally, do you see potential for these technologies to be applied at scale in consumer markets, particularly for applications such as passive cooling?
Well, there's a lot to unpack there.
Yeah.
I think.
Question.
So first of all, we're not using quantum dots that I'm aware of. It's been a little while since I looked at the quantum dot literature, but I don't think you would call these quantum dots that we're applying onto the technology. And I remember the last part of the question was about passive cooling. We are doing passive cooling, although I'm careful sometimes to not call it cooling and call it heat mitigation, because you put the sun deflector with the TiO2 dots on the outside. I mean, in sun, because sun is, straight sunlight is 1,000 watts per meter squared, sometimes a little more. That's a big heater. And so you're still going to heat up. So it doesn't necessarily cool you below, it doesn't cool you below ambient. But it doesn't heat up nearly as much if you didn't have the dots on the shirt, or if you're wearing, some other regular shirt. But and there was some stuff in the middle there that I don't remember from the question.
I think they were kind of talking about circular, sustainable approach.
Yeah, so we get
Coding.
that question a lot as well because of the interest in the industry, and I would tell people with the approaches to chemical recycling, if you really want to do that, which that's a lot of energy, that's your call. That adds a lot more emissions than using virgin materials. But if you really want to recycle the materials, you can do it using those approaches, because you can just filter out all the technology we apply to the surface, because you're taking things back to the monomer anyway, right? So that's not wrong. In fact, we actually did a little demo project where we did that with our OmniHeat reflective. So yes, you can do that if you want to. It's not clear to me that makes sense for economic or for environmental reasons.
The next question is from Renika. I was wondering, when taking thermal images of surfaces containing fabric and metallic patterns, do you make any adjustments to compensate for the difference in emissivity?
Great question. Yeah, clearly someone who understands that what you're actually measuring with a thermal imaging camera is something called radiosity. Yes, we do. We take that into consideration, because if you don't, you're misreading the results for sure. Great question.
Yeah. Well, we'll hang out for a minute or so. These were all the questions we had so far.
Okay.
I think just going through all these questions and understanding the technology, it's been so interesting just to do a deep dive into how materials that can work for a human microclimate can also work in space. So it's a very cool way to relate to, next time I look at my jacket, I'm probably going to not just treat it as just a jacket. It's definitely a cool piece of technology.
Yeah. No, I appreciate that. And one thing I would add too, and I can't remember if I said it during the presentation, is that, everything I was talking about was sort of what we refer to as surface thermal optical properties, right? And so, for example, and for textile multi-materials, it's not uncommon to mix, for example, ceramics. I think most synthetic fibers, if not all synthetic fibers, have some degree of TiO2 or some other ceramic, mixed in at a low level, because you can't put too much into fibers, because you start to affect the physical properties, the tensile strength and things like that. But you can load stuff into fibers, and that will affect things like emissivity, absorptivity, reflectivity, as some of you, if not maybe all of you, know. But you're limited with how much you can do there. First of all, you're limited in terms of the range that you affect the surface, because whenever you put something in a polymer and you extrude it into a fiber, those additives are throughout the cross section. And so you've got some close to the surface, some in the center. And there's, what we call the question is, what is the surface? Is it the first 10 angstroms? Is it the first 10 nanometers? What is the surface? And there is an answer there, but I don't really know what it is, and it probably depends on the materials you're mixing together. And so I just wanted to state that, we put these things on the surface on purpose, because you get the biggest effect that way. But it does change the appearance, and not everyone likes to have dots of something on their garment that they're wearing. But you get big changes in performance in terms of heat reflection, heat absorption, heat emission if you're trying to do cooling things. And so there's still plenty of work to be done if you figure out a way to make these big changes in these radiative properties while having more flexibility in terms of the aesthetics too. So
that's a very good point. I think that was the end of the questions. Haskell, your email is on the slide, so thank you so much for spending some time with us today. I learned a lot.
thanks for listening.
Yeah, I know a lot of us on the call learned a lot. And if you have any additional questions for Haskell, please feel free to reach out to him. And thank you everyone for joining the materials interest group. This is a recorded session, so we will post it. And I know our AATCC staff will be sending us emails with a link to it. Thank you to the staff as well. It was, thank you for putting it all together. And I hope everyone has a fun, safe, and restful long weekend.
Thank you, everyone.
Thanks.